All right, so we got both Discord and YouTube streaming already. If you have any questions to ask, now is a good time. We got about 2 minutes before the class starts at noon. And as some of you already noticed, I'm leaving notes and also sharing exam one with some people, so that they can see the grading process. Not really sure whether you guys can see my comments or not, because I'm only sharing you as a viewer. But not the entire class has that yet, so it is still in progress. Nope, it is not fully graded. Oh, okay, thank you. So I might need to share with you as a commenter so that you can see my comments. Okay. Alright, so we got about 1 minute, less than 1 minute before the class starts. And what we'll do today is to continue our discussion of the U function that we talked about the omega function, and today we'll talk about the U function, which generates all the combinations as opposed to all the permutations. So there we have it. About 20 more seconds to go. Alright, let's go ahead and get started. The first thing, so there are a few things that we need to get out of the way first. The first one is next week is spring break. And as you can probably tell, I'm not terribly excited about spring break, because what it does is, it introduces a whole week of non-activity and break up the momentum of the semester. So, I think that is actually not too helpful. Yes, I can go over the previous homework. And I got a direct message that, well, unfortunately, late is late. We got a whole week to work on this, and that's 168 hours. I can't really do much about being late in this case. Alright, getting back to the class. Alright, so there's also one more thing that I want to talk about, which is after spring break, we will have our second exam, because it's gonna be about week 11 if we don't count spring break. So that means on Wednesday we're gonna have a practice exam, which is basically just exam 2 from the previous semester. And once again, there's no guarantee of how close your exam may be to the previous semester. All I can say is, I'll give you a sample from the previous semester for exam 2, and I'll go over that one. So I know someone is gonna want to have a study guide. I don't really have a study guide. I mean, I never really used a study guide as a student. I just basically go over all the material, make sure I have a thorough understanding of the material, and that's kind of how I prepare for exams. I know my method may not work for everyone, because some people think differently, they process things differently, and so on. But I just want to let you know that as a student, I never asked for or utilized study guides. So So that's probably useful data for you. All right. So we're going to go over the U function today, and then we'll go ahead and talk about the. Oh, right. We have to talk about the homework. So let's go ahead and talk about the homework first. All right. Yep, I try to remind people don't wait until the last moment and alright, so there we go. This is the homework assignment. And I got a few people asking questions over the weekend. And that's good. I mean, I really prefer people to ask questions, early on and try to get a confirmation of their understanding of the material ahead of time. So let's go ahead and I'm just thinking about whether I should use the tablet or whether I should use a notepad for this. I'm just going to use a notepad because I can type faster than I can write. Alright, so we'll get a notepad here, and there are two questions. I thought it was okay. I'm not going to say it. So there are two questions. The first theorem to be proven is this. The second theorem is as follows. Okay, so there are two parts to this question. There are two proposed theorem. Okay, so each one needs to be kind of treated separately, even though we can use exactly the same approach on both. Alright, so we'll talk about the first one. Okay, so we'll say part 1, and I'll call this phi. Okay, the proposed theorem is phi, and phi is T implies S and R. Okay, so the multiplication notation in this class, in the context of a Boolean expression, means conjunction. Alright, so let's see how we can process, phi so that we'll be ready for resolution. So the first thing we need to do is to look at what is the negation of phi. So that would be the negation of T implies S and R. And I'm going to put the equal sign down here, so this way I don't have to redo a whole bunch of indentations. There we go. And the first thing we do is to get rid of the implication, which is the negated portion of the first part, and then we have a or, the second portion. The second portion is not negated. So when I write something like this, I am using the implied priority of operators. And in this case, the conjunction has priority over the disjunction, and the negation also has the highest priority. So that's kind of the same, priority level as C, C++ uses. I'm just going to change a little bit of my mic setting because I think it's a little bit too sensitive right now and it's clipping. So I'm going to stop that clipping by reducing the sensitivity a little bit. Alright, so we'll give this a try and see. Oh, it's still clipping. Let me reduce it a little bit more. There we go. Alright, so getting back to here. Alright, so now what we can do is to there's not much to do at this point except for De Morgan's law, right? Because we have this negation that is applied to this or, so we have De Morgan's law. So with De Morgan's law, we basically end up with two terms, which is not T, and the negation of SR. Because each individual component inside the original OR is negated, but but those two negated terms are ended together instead of originally ORed together. That's the application of De Morgan's law. So now we use simplification, get rid of the double negation. So we have T on one side, and then we have the negation of S and R on the other side. So we apply De Morgan's law again. This time we have not S or not R. And that is done. Okay, this is in CNF already, because each term is basically a disjunction. If someone says, but T is not a disjunction, fine, make it a disjunction. Because you can always or false to make something a disjunction, or at least it has the or operator explicitly in it. Okay, so now it is a CNF. And then what we do is we create, what I call in my notes, the super CNF, which is the concatenation of everything that is known to be true, which usually I call this psi in my notes, not to be confused with the Korean pop star. And then we have to concatenate the other part, which is from the negated. This is the CNF derived from the negated proposed theorem. And now we want to see what kind of resolution we can do. So resolution is about locating a disjunctive term, locating two disjunctive terms where one has the negated variable and the other one has the same variable but not negated. So we do it systematically. Okay, we look at this term and then we ask, can we find Q on the other three terms? And the answer is no. Can we find R on the other three terms? The answer is no. Can we find S on the other three terms? And the answer is also no. Now we look at the second term, and then we compare the second term with the third one, and we ask, can we find Q? Nope. Can we find R? Nope. Can we find not T? No. And then we compare to the last term, ask the same questions, and the answers are no, no, and no. So now we look at the third term, and then we just have to compare this one with the last one, which is asking, can we find a not T? The answer is no. So there's no resolution possible at this point. Okay, so the super CNF cannot resolve to false. Therefore, phi is not a theorem of. Well, I mean, if you give the if you give this portion a name of psi, then you can say this is not a theorem of psi. But if you just leave it as phi is not a theorem, that's fine. Okay, that is understood. All right, moving on to part 2. So part 2 has basically phi, being a different theorem. This time we have Q and R implies T. So the first thing again is to look at the negation of phi. So this time we look at the negation of phi, and the usual first step is really just to introduce a negation on top of the entire thing. And I'm just moving my mouse pointer over to Discord and see if there are any questions. Nope, there are no questions at this point except for direct message. Okay. All right. And then getting back to the class, because sometimes people ask questions in the direct message channel, and this is not one of those cases. All right. So the first thing to do is to get rid of the implication. So we have QR, the negation of QR, because we have to negate the left-hand side, and then we have the or of the right-hand side. And now we do have a choice, because you can apply De Morgan's law, the innermost portion. You can apply De Morgan's law with this part first, or you can also apply De Morgan's law on the outer part first. It doesn't really matter, which way you do it. If you do it, it really doesn't matter. Okay, so we'll go ahead and apply it to the outermost outer portion first. So we end up with the negation of QR and the negation of T. In other words, we are distributing this negation over, okay, let me move the mouse cursor over this term and also over this term, but then we have to change the operator from an or to an and. So now we have, and then we perform simplification. So not just kind of goes away. We have QR not T. And then at this point, we can say it is just QR not T. Basically, parentheses are no longer needed in this case because now we have a CNF. And for people who are not, who insist, a disjunctive term must have a disjunction operator, fine, we'll do it like this, right? So now we have a CNF. And then what we do is we just use the same approach as last time. We make a quote-unquote super CNF by concatenating everything that is known to be true as a CNF, and then plus, okay, concatenate the CNF that we just derived from the negation of phi. And now we basically ask the same questions again. Now, in this case, for some of you, if you can spot, like, oh, I know exactly how to do this to get to the contradiction very quickly, fine, okay, it's not a problem. But I personally prefer methods that are more systematic, so that if I want to program a computer to do the same thing, it wouldn't be too hard to do it. So the systematic method that I usually use is to look at the first term and then compare it to the second, third, and so on, and find out, can we do any resolution? So the first one that can resolve with the first term is the Q term all by itself, and then we'll be left with not R or not S. So after the first resolution, and I'll highlight which one, how I'm doing the resolution. So we have the not Q over here to match up with this Q over here. And as a result of the resolution, the super CNF gets longer. And this is also why I really kind of want people to do this using a computer, because when you do this by hand, obviously this is going to be extremely tedious. Alright, so now we look at, we try to compare the first term to other terms, and we say, can we find a R? And the answer is, yep, there's one R over here. So we'll do that resolution too. So we'll say this not R is matching up with this R over here. And then we copy and paste, and then just make a new term at the end of the new conjunction, or the new CNF. Okay, so now it gets a little longer, but I don't need to refer to the question anymore. So now we have not Q or not S left from the first expression. The second one, basically has a not or false left, which basically just kind of simplifies away. So now we look at the first term and ask, can we find an S term from the rest? And then the answer is no. So now we look at this term here and go like, woohoo, we can look at this and it does match up with exactly the next one. So you can see, this is taking a little bit longer than most of you use, because most of you can kind of spot, how we can get to the resolution or the contradiction as quickly as possible. But I'm just doing this, in a much more systematic way, so this way I don't miss something. Okay, and then we look at this not R, and it does match up with the R that we saw earlier, which is this one over here. And then we just do another resolution, which is copy, paste, and then add the new term, the result of the resolution, and that is going to be not Q or T. So that's a new term. So every time we apply resolution, the new term, the newly created expression is basically appended to the original one, so that also can be used by further resolution. Okay, so now we look at this particular long expression and we ask, can we find a not T? And this time, yes, we can find a not T indeed. So this T is going to resolve with this not T over here. And yes, so if you use this kind of mechanical process, it does get very tedious. Alright, so after this resolution, we get not Q or not R, because the not T term has basically just or false. So that gets simplified out. And then we ask, can we resolve this t with any other not t? And then the answer is no. So now we move on to this q, and we ask, can we find any not q to resolve this one with? And the answer is yes. Okay, we can find the first not q is over here. So this is basically the most tedious way to do this. If you can spot the where you can generate the false quickest, you can go ahead and do it that way. But I'm just going through this the slow way of doing this. All right, so now we look at this q and say, can we find any other not q? And there's one more, two more actually. There's one over here. So this also resolves to just t by itself, and t by itself does not exist yet. So it's a new term. So now we basically say, let's paste it to the end. So we get the t here. So for those of you who can say, okay, I think we can stop here. Okay, we'll go ahead and just stop here, because we can see at this point, we can already see there is a not t, which can then resolve with the t over here. Yes, I broke the order. I'm no longer doing this in the very systematic way, because I think you get the idea. Okay, so now after this resolution, we get a 0, we get a false. Now because this false is ended with the rest of the super CNF, so we basically have blah 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 and false. But anything and false is just false. So we'll say this entire thing becomes false, and then you have to make a conclusion out of this too. So we can say, since psi and not phi is false, phi is a theorem. Okay, or something to that effect. So that would be the full answer of the homework assignment. Do we have any questions? All right, I'm not seeing any questions. Then we are going to move on to the u function. All right. Oh, there's one more thing that I want to kind of remind people. In the exam, in the first exam, and also in all future exams, in the instructions, and I mentioned that in class too, was do not copy and paste from an outside source. That means no copy and paste from an outside source. So what do you think I would do when I see a copy and paste of pretty much the entire document from an outside source? I cannot make an exception. Okay, so that's basically there's not much I can do. I mean, if the instructions specifically say do not do that, and someone decides to do it, either because that person did not see it or decided to do something else, I can't really make an exception and go like, well, I guess it's okay this time. That's an interesting question. So Li Yu asked, is it possible to prove a theorem using disjunctive normal form DNF and prove it true? It depends on what do you mean by prove it true. Depends on what that it is referring to. Because in the CNF method, we are combining everything that is known to be true, which we call psi, and also the negated theorem, and we are basically making use of proof by contradiction to get it to work. So when you're using a DNF, it depends on how you generate that particular DNF. And a theorem cannot be proven by combining the theorem itself and everything that is known to be true and have that to eventually lead to a true. That doesn't work. Because if A implies B, okay, if A does imply B, having A or B does not guarantee a 1. Let me think about it. If A implies B, then not A or B is true. So if A is true, then not A is false. So it doesn't matter what B is. Yeah, so that doesn't work. I don't think it is going to work. All right, so Yolanda has another comment. And while we are waiting for Yolanda, we're going to go to the U function. That's I think that's what we just said. Was I do not know, but I don't think so. I don't think DNF is useful in the context of proving a theorem. Now, DNFs are useful in other contexts because depending on what type of circuitry you're using, there are things called TQ. Okay, what is the name of that thing? I cannot remember. These things, I used to work with on a daily basis, and now I cannot remember those names. So we have PALs, we have programmable logic. Okay, the best way to put it is we have programmable logic. Some programmable logic are based on OR gates or NOR gates. Some are based on NAND gates and stuff like that. So it is useful to be able to convert any Boolean expression into a DNF or CNF depending on the underlying mechanism of the programmable logic. So from that perspective, DNF can be useful, but from the perspective of propositional logic, DNF is not useful because it doesn't help us prove a theorem using proof by contradiction. So I think that is probably the best conclusion that I can give. All right. So now we're moving back to the U function. So the U function has a base case of U of 0 of x, x being the set of all possible outcome, for the first trial, is the set of an empty set. So now we want to kind of see if this makes sense. I'm hoping people have read this over the weekend, after our discussion on last Wednesday about the omega function, because this is really a kind of a shadow of the omega function, except this one is actually easier despite it looks really horrendous. Does it make sense? Because the 0 means we have 0 trials. So I'm basically saying here is a bag of some marbles, okay, and the marbles are numbered or otherwise they are distinct from each other. Each marble is distinct from the rest. And then I'm asking you how many ways, show me all of the different ways to choose nothing out of the bag. So imagine that you have one bag to hold everything that you have picked out of the other bag, and I'm asking you how many ways can you choose nothing and put nothing into this new bag from the bag that already has all the marbles. The answer is there's only one way. You just end up with an empty bag that was given to you. That is why we have a set of an empty set. Okay, the outer set is basically saying this is the set of all the outcomes from the experiment, but the empty set inside the outer set is basically saying the only outcome is an empty bag. Okay, so from that perspective, I hope you guys are convinced that this base case does make sense. So if I want to define something recursively, we have to say, well, at some point the recursion has to stop. When does it stop? The answer in this case is when we are choosing nothing out of a bag that has several items. Then we can stop and go like, that's a trivial question. Okay, if you give me an empty bag and say, pick nothing out of the other bag and put it into this empty bag, there's only one way to do it. Okay, which is basically saying I just end up with an empty bag. All right. So now what we do is to look at it recursively. So the recursive way looks really confusing because I'm using the big U notation, which is a union of a series of items. Okay, so I'm using that notation that makes it a little bit harder to read. So the UI of X is asking, what is the outcome set of picking I things out of the set of X? And in this case, ordering is not important. Okay, that's why we are talking about combination, because from last Wednesday, we learned that in combinations, ordering within a combination is insignificant. But when we talk about permutations, then when you have permutations and the ordering of items in the permutations are different, then they are distinct permutations. Okay, so those are the things that we talked about last Wednesday. So now we look at this and we go like, okay, can we use an example to work this out? Can we do something like what we did last week, which, oh, okay, I just passed the window here. Can we do something like this, but this time we are using big U2 of ABC? Well, the answer is clearly yes, right? I mean, that's kind of the whole point of, doing this example so that you guys get an idea of how this works. All right, so now we're going to get started, and let me make sure that I turn off swiping, because otherwise I have a bad habit of kind of using my palm to swipe on the tablet. So if I don't turn it off, I'm just gonna I end up swiping to the new page. So the first thing I'm gonna do is really just to copy the equations. So I'm gonna write down here U2 of A, B, C, and I want to figure out what this becomes. All right. So what I do is I look up the definitions. I look up the base case and go like, well, can we just stop right now and say it is a set of an empty set? The answer is no, because the subscript after the U is not a 0, it is a 2. Then you go like, okay, fine, we'll do it recursively then. So now we look at this recursive definition, and the outermost big U notation says for each E in X do blah blah blah. Okay, so we want to basically go through those iterations first. Okay, so now we go back to here, and I can still display both at the same time, so this way you can see how I am expanding it. So now we say, okay, I'm using comments here, but I have to make sure the comment is visible where you can see it. Okay, so here's a good spot. We say, well, let's say E is A, let's say E is B, and let's say E is C. In other words, we have 3 iterations for each E in X loop. Okay, so now we say, okay, what does each iteration look like? So each iteration is basically looking at this portion of the original expression and say, okay, now that we know what E is, what does this thing look like? Okay, so we'll now say, okay, we still end up with a big U notation, but this one is a little bit easier. Okay, we have uppercase S in, and then we have big U of I minus 1, but since I is 2 in this case, this is U1, and then inside the parameter of this U, we have X minus the set of E. X is referring to ABC, and E in the first iteration refers to A, so that means we can include everything in ABC except for A, so we only get B and C left. So here we have B, C left, and that is not it. That's not entirely it, because we also have to say, what do we do with each term? So with each term, we basically look at E, which is A, and put it into its own set, and then we have a union with the big S, which is this variable here. Okay, and that's it. Okay, now we say we union this with the next one. So the next one looks about the same. We have big S again in U1, and this time E equals to B, so we have A and C left over here, and then we the set that we're constructing on the fly would have B by itself in a set union with S. So you have to understand that this particular S here is a local variable. It is local to the loop that we are creating because of the inner big U notation. So let me switch back to Discord and see if we have any questions. The answer is nope, there are no questions. Okay, so this is going to be union with the same similar thing, except this time E is C, so that means in the set of U1 we have only A, B left. And then we make a set out of C, union that with whatever S becomes, and that becomes the first level. This is the top level expansion, and now we want to look at each sub level of expansion. So now we say, okay, so what is U1 of, I'm just copying from this part here. Oh, okay, that's not what I intended to do, so let me erase what I just did. There we go. Okay, so we just want to do this one. So now we have BC to choose from, and it has, this experiment only has one single trial, and we want to find all the outcome of this particular one. Now some of you can look at this and go like, oh, we know what this one looks like already. Okay, intuitively we know. But since we are trying to do this mechanically by using the definitions, we are going to do it kind of, using the long way of doing this. So now we look at each iteration. E is B for one iteration. E equals to C for the other iteration. Now whether we use C's first or B first really should not matter, because remember, it is a set. And as a set, there's no inherent ordering between the elements inside the set. So whatever way we want to do this, as long as we cover all of the elements inside the set, BC in this case, it is actually okay. Alright, so now we basically use this notation again. So this time we have U0 of a set that is based on BC, but B cannot be in it. So it only has C left. And then we have B in its own set, and union that with whatever S is that is coming as an element of U of 0. And then this is going to be unioned with U, oops, said one thing and wrote something else. U as in U of 0. And then this time, because E equals to C, we include everything in BC except for C. So we only have B left. Okay. And then for each of this union, big union term, we generate a set that contains C in it. But we also want to union that with whatever S is. Alright, are we still doing okay in this case? I'm looking at the text channel. Alright, cool. So if you think this is super duper tedious and it's just a whole bunch of nested application of functions and stuff like that, it really is. Okay, it's as mechanical as it possibly can be, because we want to eventually be able to program this. So things that are mechanical is good news. Okay, even though it takes us a long time to do this, the computer can get through this really quickly. Okay, and it becomes easier to write the algorithm. The more mechanical it is, the easier it is to automate it. All right. So now we get down to U0 of something, right? So we have U0 of C in this case. Okay. And then you go like, but heck, it doesn't even matter what we have in the parameter, in the argument, because according to the way we define U0 of something, X is irrelevant when we want to come up with the answer. So this one is really just a set of the empty set, and so is this one. That is just a set of the empty set, right? Okay, so how is that going to help me, right? So the way this is going to work out is going to be, so now we take u0 of c, which is this thing here, and then we substitute it back into this spot here, and then we just say for every element in this thing, we want to combine that thing with the set of b. Okay. So are we doing okay? Do you guys want to finish this? Go one step further, or do you guys want to just go like, yeah, we get it. I'm not sure. Okay, so finish it. Okay, let's finish it. Very good. And so now I'm gonna be a little bit lazy, because what I'll do is I don't want to overwrite this portion, so I'm just gonna copy and paste it. So this way, I can let you, I can show what we are substituting. All right, so and that's what we want to do. All right. Okay, so I think we are good here. All right. All right, so now that we know u0 of c is a set of the empty set, so we take it and then we substitute this thing here, because we just figure out what that thing is. So that thing is just a set, oops, okay, wrong tool. So that thing is just a set of the empty set, and same thing over here. So that is just a set of an empty set, like so. So this is really just, kind of back tracing, because once we got to the lowest level of the recursion, now we are backing out. We are backing up, to the earlier points. All right, so now what does that look like? Oh, that's not an equal here. It's not an equal here. Sorry about that. All right, so now we want to look at this and go like, okay, this one is basically saying for each element S of this particular set, generate a new set like this, and then have a union of all of those, right? So if we expand this, okay, it becomes, because there's only one element in this set here, so when we expand it, it becomes really just B in its own set, unioned with the only thing which is an empty set over here. And then this whole thing, okay. I turned on the pinch method, and that's why it kind of zoomed in. All right, so that is now unioned with the set that has C in it, unioned with also just the empty set. But we also know anything union with the empty set is just, that thing itself, okay? Because, the empty set cannot contribute anything in a union operation. So now we just end up with the set of B and the set of C as elements of the actual result of U1 of BC. So let me pause here and see if we have any questions. And if you do have any questions, you can do a screenshot on just the portion that you have a question about, and then paste it into the text channel. That would be the easiest way for me to see where you want me to focus the discussion on. This is also why I think Discord is great. Why aren't B and C union? Okay. Because they are individual elements. What does S represent? S is just a local variable that is going through, whatever U0 is generating. I'm not sure whether I answered Jack's question or not. So the introduction of s as a variable is from its own definition, from the original definition. If you go all the way to the notes, so if you go all the way to the notes here, uppercase s is introduced here. And it is basically saying, okay, let's first compute u of I minus 1 in parentheses x minus the set of e by itself. And because u of blah 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 is going to generate a set of sets, so now we just say, okay, for each element of what the big U function generates, do the following. The following is referring to this part of the expression, and then we just make a big, huge, gigantic union out of those things. So that's, oh, okay, so Jack is getting it. Okay, very good. So getting back to Anita's question, so what we'll do is we're going to do this step by step. Okay, so this becomes the set of B unioned with the set of C, like that, right? Are we good so far? Because anything union with the empty set is just the original anything, right? Are we good? Are we good here? Are we good with this part of the derivation? Okay, all right. So now we take a look at this and say, should we end up with BC in a set like this? And I put a question mark here because that is what we want to figure out. So what do you think? The set that contains B is an element. The set that contains C is an element. There's no interaction of the element because the union applies to this set and this set. The union does not apply to whatever the elements are inside those particular sets. And that's why the set of B and the set of C do not interact at all. Okay? All right, so very good. So we now know the answer is no. There's no equality here because we are not performing the union for the elements of the sets on the two sides of the union operator. So we are not performing union recursively to the nested sets. We are just performing the union on the outermost container set in this case. Okay? So now that we know U1 of BC as a set, it's really just boiling down to the set that contains B and then another set that contains C and then both of those inside and outer set. How many people feel that it is necessary to look at what is the next one? AC. And expand this one, just like the other one. I'm hoping you guys are feeling okay that we don't have to expand this one, because the structure of expanding is going to be exactly the same as what we did earlier, except instead of BC, we end up with A in its own set, B in its own set, and then the whole thing in its own set. Is that okay? Or is it okay for me not to fully expand this one mechanically and just get to the answer? Okay, all right. So I'm just going to say this ends up with a set that contains A in a set and C in a set. And then U1 of AB is going to be a set that has A in a set and then B in a set, like so. Okay? So now what do? We do the substitution, right? We go all the way back here because what we have just figured out is this thing here, which is supposed to go here, this thing here, which is supposed to go here, and then this thing here, which is supposed to go here. So are we still doing okay? All right. So I'm going to back substitute things, but first, I'm going to copy and paste a few things. So this time we do need to set a new page. And I'm going to turn on swiping for now because I do need to go between the two pages a little bit to get this to work. Alright, so we need the selection tool because I need to take the original thing like this one, and then we do the substitution on the next page. So we have a copy and then a paste here, and then put it, that would be a good place. And now we go back to this part, and now we want to expand what is U1 of BC, okay, this time I swiped unintentionally, and U1 of AC and then U1 of AB. So we kind of know how to expand. So instead of copy and pasting the expansion, I'm just going to write down the expanded version over here. So this becomes a set. Oops, wrong tool. Alright, so this becomes a set that has B in its own set, C in its own set, like that. This becomes a set that has A in its own set, C is in its own set, and this becomes a set that has A in its own set, B in its own set, like so. Okay. So are we still doing okay so far? Because all I did is to say, okay, now that we have figured out all the U1s, we'll just kind of plug in the values of the U1s back to where all those U1s were first referred to. Are we still doing okay? All right. And now it gets a little bit more complicated because each line, okay, now I have to turn off swiping because I just swiped accidentally. Oh, okay, it's this tool, turn off swiping, and go back to the writing tool. There we go. Alright, so now we have to kind of go like, okay, because we do have multiple items in each one of these sets, so now the first line expands to the set of A unioned with B, and then this thing unioned with the set of A unioned with the set of C. Okay, is that okay? Does everybody see how this thing here expands to this thing over here? So we're good? Okay, very good. And we do the same thing with the second line, and it is B unit with everything. For each item of S here, we created this union. So the first one we pick is just A as a set, and then we move on to the second item, which is C. So we now end up with B unioned with C over here, and that in return is unioned with the set of C unioned with A, and then union, this union is from this union over here with the set of C and the set of B in this case. Whew. Okay, we're still doing good? Because this step is just expanding the big union operation on each line into the individual items depending on how we iterate through S in this particular set. So now we actually perform the inner unions. Okay, so this time we are indeed, this union does apply to the set of A and the set of B. So this time we do end up with a set with AB in it. Okay, so now we have AB in this particular set, and now we have AC in its own set, and then we have BA in its own set, and then we have BC in its own set, and then we have CA. Oops. Yep, CA. Yeah, penmanship is really bad. This reminds me of elementary school. I probably will be asked to practice my penmanship. Like hundreds of times. Okay, there we go. Whew. Alright. So now we look at this gigantic union and we ask, how many things should we end up with after this, after we do the entire union? Alright, so now let's look at this union here. This union applies to this particular set against this particular set. Okay, so that is not hard. Okay, so we have I'm gonna do this in a slightly different way. Okay, so we want to see if there are overlaps, because if there are no overlaps, the new big gigantic union would just have 6 items in it. But if there are overlaps, then it's gonna have fewer than 6 items in it. So we identify that this AB and this BA are really the same thing. So the end result is gonna have just one of them, because the set of AB and the set of BA are exactly the same thing. So they're exactly only 3 elements. Yes, Anita is correct. So we have AB, and then this AC is really the same thing as the CA. So we just pick one of them, right? And then this BC and this CB are really the same as well. So we just have BC, we just choose one of them, and that becomes the answer. So in many ways, it feels exactly like permutation, except at the very end we have a union operation instead of a Cartesian product operation. And the union operation, basically says, well, if you have duplicate items, remove the duplicates. Okay, only in each set, each element has to be unique, and that really is the main difference between the omega function that finds all the permutations versus the U function that finds all of the combinations. All right. So I'm going to pause here because we have just gone through the mechanical process of applying the definitions in section 7, and I want to see if you guys have any questions. If you guys don't have any questions, then we can kind of move on, but if you do have questions, then we're going to stay here for a little bit until we are okay with all of those concepts. All right, I'm not seeing any questions. All right. Okay, so if there are no questions, we're gonna go back to the Lotto game, okay? Because we want to be able to analyze the chances, even if the Lotto website does not give us the chances data. All right, so we do want a new page this time. Or if a new page is already generated, we just need to go to the new page, which is page 49. There we go. All right, so now we go back to the Powerball Lotto game. So in the Powerball Lotto game, I think we choose 5 numbers from the set going from 1 all the way to 69, and these are called the lucky numbers. And then we choose one number from the set from 1 to, I think it's 29 or 26, I cannot remember. Does someone know right away, or I can always just look it up. Okay. Oh, 26. Okay, thank you. All right. Now, this plus here is really a misnomer. This should be a Cartesian product. Oh, you guys cannot see it. I forgot to switch. There we go. So we want 5 numbers from this, and we also want to add here and say order is not important. Okay. So we want 5 numbers from 1 to 69. Ordering is not important. So that means 1, 2, 3, 4, 5 is in a set, and that means 1, 2, 3, 4, 5 in a set is exactly the same as 5, 4, 3, 2, 1 in a set. Okay. So that means we have to use the U function to generate just this part here. But whatever that part has, we have to use a Cartesian product to combine that with this portion, because the Powerball number is independent to the lucky numbers. In fact, we can have the same number that was previously in the lucky number, and it can also double as one of the as the Powerball number. Okay, so that is entirely possible. So now we want to know how many tickets, how many possible unique tickets can be generated based on these rules. So you don't even need to use the use function, because we just basically say, oh, this portion, okay, if we look at this portion as a set, so we know the cardinality of U5, because we have 5 trials. Each trial is picking up one of the 68 numbers. And we also know initially we have 1 all the way up to 69. And we know, since we're only interested in counting the number of tickets, so we don't need to actually look at the set itself. We just need to know the cardinality of that set. Now, this relates to something that we talked about on last Monday, which is how do we count combinations. So in this case, it is 69 choose 5. If you were to use a spreadsheet, this becomes combin of 69 5. Okay, which is a fairly big number. Okay, but we are not done yet. Okay, because the second one, is this one. You can look at it as a permutation, or you can look at it as a combination. It really doesn't matter, because when you have a trial number of trial of 1, they become the same. Okay, so so now we have we can use U1, okay, of the set from 1 all the way up to 26, which is 26 choose 1. And this is basically the same thing as 26 itself. Alright, so the actual number of possible tickets would be 26 times the combin, or the number of combination of choosing 5 out of 69, which is a fairly large number. Now we want to double check, right? Because TAC claims this is the answer. So I claim that combin, if we were to use a spreadsheet, 69.5 times 26 is the total number of unique tickets. So which basically becomes the chances, because on the lotto site they say, the winning chances is 1 in blah blah blah. So that blah 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 should be this number to get to the jackpot. So now we want to do some double checking. So the first thing we do is to use a spreadsheet to do this calculation. And for the most part, I don't use a calculator these days anymore. I just use spreadsheets, as a calculator, because a spreadsheet allows you to run through multiple, scenarios, reusing formulae and so on and so forth. So it's really just handy to have. Okay, so I'm just going to hard code this one, which is combin, what was it again? 69 choose 5. Oops, I said 5. There we go. Times 26. So it came up with this value, which is 292,201,338. And now we want to see if this is also the chances that the Powerball site is quoting. So we go to This one, this is not the California one, but I think the rules are the same. But just to be sure, we say Powerball California State Lottery. And it is exactly the same. All five of five, those are called the lucky numbers and matching the Powerball number. So there are 292 million and something unique tickets. So that tells you, if you know what the jackpot is, that kind of gives you an idea of, whether it's worth it to play, to buy a lotto ticket or not. So a lotto ticket, if I remember correctly, is $2 each. Is that correct? I don't know. I don't play lotto, so I don't know for sure. I think it's $2 for each ticket. So assuming it's $2 for each ticket, and if you look at the prices, okay, I think the last draw. Okay, so the price amount is 200 million, and we have 290. What was it again? 280. No, I cannot remember. I'm really bad with remembering just numbers for the sake of remembering number. 292 million. There we go. So definitely not worth it, right? I mean, because it takes $2 to buy one ticket, and the chances of winning is 292 million. So that means the chances is definitely against you. So the question now is, when is it a good time to buy a lotto ticket? And somebody's going to say, well, since it takes $2 for each ticket, so when the prize money is exactly twice of this value here, then it is worth it to buy a lotto ticket. Okay, so we'll say 2 times this. The 2, is accounting for $2 for each ticket. So when the prize money, when the jackpot, prize money is 584 million and something, then it's worthwhile to buy a single ticket for $2. But that really is not the case. That really is not the case, because you're forgetting that you have to pay state and federal taxes when you win the lotto. So accounting for that, okay, I cannot remember how much. I don't know, because I'm not that wealthy. What is the tax bracket when you have an income of some $584 million? Let's call it 50%. Okay, combining state and federal tax. Okay, so now you say, well, we can always account for that. Okay, so maybe when the prize money, when the jackpot is $876 million, then it's worthwhile to play this game, because now I have accounted for the taxes that I will have to pay, after I win the lotto. But you're forgetting one other thing. When the jackpot is this much, you wouldn't be the first person who says, oh, it's worthwhile to buy a ticket. So that means there can be multiple people with the winning ticket. So now you have to split the winning money with all of those people. So here comes the biggest question. Okay, this is the most difficult question to answer: is how many people would end up buying the same ticket? Okay, Lee, you just posted something, and over here, since California Lotto withholds 25% of the winning for U.S. citizens and resident aliens who provide a security number, 28% of the winning for U.S. citizens and resident aliens who do not provide a social security number for the IRS, you have to pay the remaining 12%. I don't understand what the remaining 12% of what. So they withhold 25% of the winning for U.S. citizens and resident aliens who provide a social security number for the IRS. You have to pay the remaining 12%. Okay, there are some comments coming here. All right, so there are a bunch of people typing right now about how to interpret what Li Yu has quoted. But okay, so regardless, okay, now I'm not downplaying the discovery of Li Yu, but I'm simply saying this part is calculated. This part can be calculated. Okay. Now, after this part is calculated, okay, you still have to think about how many people would end up with exactly the same, jackpot winning ticket, because it is possible. Because the state lottery does not guarantee that after they have sold, they do not guarantee uniqueness of all the tickets. In other words, they are not just going to sell exactly 292 million and something tickets. They will basically, every time a person says, okay, here's $2, I want to buy a ticket, they just randomly generate a ticket, or supposedly they're supposed to generate a ticket randomly at that point. So that means more they can sell more than 292 million tickets if there are enough people buying those tickets. So now the question is, how do you know, how can we model, how many people have bought tickets, or what is the total number of tickets sold? Yep. So how do we model that? That number, I believe, is not released on the website, but you can infer that. You can actually calculate that. So our next task, okay, for the next 10 minutes is to try to figure that out. Okay, so let me just read the text messages on Discord. So, in the price. Okay, so Angel is correct. All right, so let's think about that. Okay, let's think about that. So we look at this particular one, and let's see, past winning numbers. I think this is a good one. Okay, so we look at this one and go like, okay, if the prize money is high enough, okay, I can go to the bank, right? Talk to a loan officer at the bank and say, sir, or madam, I'm gonna borrow some money so that I can buy every single possible ticket, for the lotto game. So this way, I'm guaranteed to win the jackpot because I have just bought every single possible ticket, right? Okay. And then the banker says, well, but how do you? So your plan is, after factoring out, the tax consequences, after factoring out, how many winning tickets there are, how much you have to spend to buy all the possible tickets, and make sure that the jackpot money can pay for all of that stuff with some money left over, because you want to have at least some money left over to do something with that money. The banker would then say, guess what? I got 2 other customers who said the same thing to me right before you arrived at the bank. Right? I mean, that can happen. So Anita may have showed up before Angel does to the same bank, to the same loan officer, and said exactly the same thing, and then took out a loan money just large enough to buy every single possible ticket, so that the jackpot ticket is in it. But now you have multiple people winning the jackpot, which means the jackpot money now has to be divided to all of those people. So now neither Anita nor Angel will have enough money to pay the bank back. Not even close, right? That would not be a very good situation, right? So now the question, so here's the big question. So the big question is, how can I know, how do I model how many people will buy tickets as the jackpot money increases? That becomes the next important question, right? So given this particular table over here, can we use this table to figure out, how many tickets are sold altogether? That becomes a question, okay? Because you want to be able to use all the past data like this, and then come up with a mathematical model of some kind to approximate, behavior of people. How likely are people to purchase a ticket based on the jackpot prize money? So that becomes the next question. We got about 7 more minutes to explain this. So are we ready to kind of use this table? Okay, I'm gonna. Okay, so let's go. Let's do this. Okay. So what we do is we can take one or more of these rows, but you have to work on one row at a time. I wouldn't use a row that only has 2 winning tickets because that doesn't give us enough data to be certain about the analysis. So I'm going to pick something like this row over here. Okay. So what this row is indicating is there are 3,432 tickets that won this particular class of prize. So each person gets $8 because they matched 2 of the 5 lucky numbers, and they also match the Powerball number. So from this number, can we infer the total number of tickets sold for this particular week of March 20th? That is the next question. All right, so now we want to see how many tickets would win this particular prize. Okay, so that is our question. And I'm going to go back to the tablet, get a new page in order to figure this out. Okay, so tablet is right here, and I want to stay on here. Okay, so I'm only going to use a portion of the tablet, and my face is also on the tablet itself, and I just have to be careful which portion I use, I suppose. All right. So now what we do is we say we want 2 lucky numbers and the Powerball number. So that's the objective. Okay, we want a ticket. Okay, we want to count the number of tickets that would match 2 of the lucky numbers and the Powerball number. So this seems simple, because we just say, oh, okay, so that means out of the 69 numbers, don't copy this, by the way. We want 2 because those are the 2 lucky numbers, and then we just multiply by the total number of Powerball numbers, which there are 26. So that becomes the total number of tickets that will win the 2 plus Powerball prize money, which is $8. Okay. Nope, that is actually not the case. That is actually not the case because we're choosing from the wrong thing. Okay, 69 is representing the total number of numbers that we can choose from for all 5 lucky numbers. Okay, so given that 5 lucky numbers are already determined and we only want to match 2 of those, that means we are choosing 2 out of the 5 lucky numbers. That's why we have 5 choose 2. Then somebody's going to say, but Tech, aren't you forgetting that there are 3 other numbers on the ticket? Yes, I know. But those 3 numbers are taken from the non-lucky numbers, right? Because out of the 69, 5 are the lucky numbers, and we have already chosen 2 out of the 5. So of the non-lucky numbers, we want to choose 3. There are 69 minus 5, which is 64 non-lucky numbers. So we are choosing 3 out of those. Okay, so this is really kind of tricky because this is the trickiest part of analyzing the number of lotto tickets, is you have to separate the lucky numbers from the non-lucky numbers. Of the 5 lucky numbers, we only want to match 2, and then we have to choose the other 3 from the non-lucky numbers. Now in this case, we also want to match the Powerball number, and because there are 26 Powerball numbers, we don't want to multiply 26, by the way. Okay, this is my bad. We want to multiply by only 1 because we want the 1 Powerball number that is the correct one. Okay, so that's why we are only multiplying by 1. So when you figure out this number, okay, we can use the spreadsheet that we had earlier to work this out. Okay, so now we have combin 5 choose 2, and then we have combin 64 choose 3 times 1. So we have 416,640 unique tickets that can win this particular prize. Okay. So what that means is if the lotto system, okay, sold every single possible ticket, and everybody who won this prize went back to lotto to claim the prize, then we would have 416,640 people showing up to say, "Hey, give me my $8," right? But we only got 3,432 people who basically went to claim. Well, I'm not even sure. I think these are the winning tickets. It doesn't mean all of these people went to claim the $8. So we only have 3,432. So let me copy and paste that number. Okay. So I paste this number here so that we can now compare those two. Okay. This is the total number of unique tickets that would win the 2+1 prize. But this is the actual number of winning tickets. So the ratio between these two will tell you the total number of tickets sold. Okay, because what you need to do is simply to look into this number and then multiply that based on the ratio between these two. So if I were to kind of guesstimate the total number of tickets sold, I would take this number divided by this number and then multiply by this number over here. So my guess is for the week of March 20th, the lotto system sold about 2.4 million tickets. And that is only in California. Yes, Ivan is correct. And this data reflect winning tickets of the same number. Yes, it does. So when people have the same number, it does reflect that. How did I do the ratio? Okay, so based on the calculation, these out of the 292 unique tickets, 416,000 would win the price that we are focusing on to get $8. But we also know that only 3,432 are winning tickets for this particular week. So we can now establish a ratio between these two numbers of how many tickets total would win that prize and how many tickets sold actually won that prize. So we are looking at the ratio of how many are possible versus how many were actually sold. So now that we have this ratio, we apply the same ratio to the total number of unique tickets, and then we end up with the estimated number of tickets sold for that week. Is that okay? Maybe. Okay. So now we want to look at this and go like, this looks kind of interesting. So can we use this to go back in past events and try to figure out a model so that we can see the correlation between the total price amount versus the number of people who bought the tickets, or the number of tickets sold. Okay, because someone can buy multiple tickets at the same time. So we just have to go back to, okay, let's say January where the prize money was pretty high. Okay, so now we just take this number, right? This is the number we are focusing on, only this row, and this time the price amount is $9. Okay, so I guess everything floats a little bit with the total amount of money. I didn't know about that part. So we copy this and then we put it into the spreadsheet, same spot over here. No, that cannot be the case. I pasted in the wrong spot. Okay, Control Z, undo this. Okay, paste it here. I think I included a tab character, that's why it went to the wrong place. So we copy and paste this over here, and we end up with this number. So for that particular week, okay, I can't read this number. Let me put in the commas. So we want to go to format. Where's format? Okay, maybe not here. Go to format, number format, and we want just general number. Okay. It's not wide enough because of all the extra commas and the. All right, there we go. So for that week, about 11 million tickets were sold. So that is still nothing compared to the 292 million possible tickets, which is kind of strange. I mean, I would think more people would have tried to buy a ticket, but you can also see there were no winning tickets for the jackpot. Nobody won the jackpot for that round either. So this is kind of interesting. So if you plot the graph of your prize money versus the total or the estimated number of tickets sold, that should be quite interesting. Okay, because you would probably see something that is not a linear curve. So it's not like when the prize money goes up linearly, the total number of tickets sold would also increase linearly. I think there's going to be a curve of some kind that has a certain baseline. In other words, if the prize money was only, let's say, $100 million or even $50 million, there will still be a base population who is going to go buy a lotto ticket regardless. So I think that explains human behavior. Alright, so we are out of time today. In fact, we are already out by 5 minutes. I'm not going to give you guys a roll-taking word for today, so there's no roll-taking. Good job being here, but I'm not going to take roll today. And I'm still thinking whether to give you the assignment or not, which is to write a program to generate either combinations or permutations. So let me think about that a little bit, and then on Wednesday I'll give you, the answer of that. Okay. Yes, I think the trademark word used by Lotto is dream. But if someone were to go to a bank to borrow money to buy all the unique tickets, and then only to find out that there are other people who did the same thing, that dream quickly becomes a nightmare, which is not good. Yeah, the really ironic part is the lotto is the money that the state makes out of the lotto game, a part of that money or a good portion of that money goes into education. So this is a how should I put it? If we run the education system right, this is supposed to be a self-defeating mechanism. Because the more people get educated, the more people take this class and understand the odds of stuff and understand probability, the fewer people would go buy lotto tickets. So it is ironically supposed to be a self-defeating mechanism. But as we can all see, that self-defeating part is yet to be seen. So something along that chain is not working right. It is funny. Yes, it is indeed very funny. Alright, so I'm gonna shut up because we are already 6 minutes past the supposed end time of this class, and I will go back to grading. Yep, so I'm gonna put some more butter on the styrofoam and start chewing. Okay, so I'll see you guys on Wednesday. Bye.